Hi, welcome to Data Structures in 5 Minutes. Today I'll be talking about disjoint sets, and disjoint sets are data structure where it allows you to record how a large set of items, known as a universe of items, is partitioned into several little subsets. And so all items in this universe are part of exactly one subset, and there's no overlap between any two sets. And so here our universe consists of 1, 12, 6, 8, 4, and 3. And the subsets, and this universe is partitioned into 3 subsets. First subset has 1, 12, and 6. The second subset has just 8. And the third subset has 4 and 3. Two operations that you might be interested in for this data structure are find, which is which small set does the item belong to. So which subset does the item belong to? And the second operation is union, which is I want to merge two sets together, and I want you to remember the new arrangement and adjust the pointers accordingly. And there are 2 ways to implement this, one that optimizes find and one that optimizes union. First, quick find is the implementation that optimizes find and makes it constant time. What you do is have all items point to the set they belong to, and each set points to the list of items. So looking back at our example here, set 1 points to 1, 12, and 6, but 1, 12, and 6 point to set 1. Set 2 points to 8, 8 points to set 2, and set 3 points to 4 and 3, and 4 and 3 each point to set 3. And so why find is constant is that all you have to do is look at the item and see which set the item points to. And so follow the pointer and it's constant time. Union, however, is not constant here. It's linear because you have to go through each element and adjust its pointer based on how the new arrangement looks. The next implementation is much more important, however. It's quick union, and this is where union is theta 1. It runs in constant time, while find is just log of the number of unions that you've done. Well, you'll see that this can be made very fast based on optimizations that we'll do in a bit, and so that's why quick union is important. Quick union, disjoint sets, is implemented as a forest, a collection of trees. So each subset represents a tree, and the trees do not have to be binary. They can have as many children as they want. Each set is a separate tree, like I said, and each set is identified uniquely by the root. So the root represents the entire set, and so when you union two sets together, one of the trees will become a subtree of the other tree, and so you lose some of that subset information that you might have with find, but the good news is that you can also find a way to get around that using a different array. But for now, let's not worry about that. Speaking of arrays, after you've visualized all these subsets as a tree, you can squeeze them all into one array, and here's how. You can have negative numbers represent the root. So the elements are the indices. You can have negative numbers represent each set and the size of the set, and positive numbers are just elements that are a member of a set, and the parent is who they point to in the tree. And all the elements only have parent pointers. There are no children pointers or whatever, or something like that. So we have a universe here of 0 to 6. And so we start off with all the elements being their own set. So each one has a size of -1, and they're negative, so that means that they're roots. Before I elaborate on this example, I'll talk about the 2 optimizations you'll make. The first one is union by size, which means that when you merge 2 sets together, the bigger set swallows the smaller set. And so this allows the tree to be much more shallow than if you allowed the smaller set to take on a bigger set. And so that's union by size. The other optimization is path compression. So what you do is you find the element, then you recursively call find on its parents, and you set all those parent pointers to the root. And so that way you can make your tree from something very deep to something very shallow. So even though find is worst case of log u, path compression makes subsequent finds much faster. And so let's draw this all out concretely in an example. So let's say I wanted to merge 0 and 1. So 0 now points to 1, and 1 is now size -2. I do another merge here. 2 merging with 1. And 2 is the smaller subset, and it gets swallowed by 1, the bigger subset. So let me do a merge somewhere outside. So let's say 5 now points to 4. So now we have this image here. We have 1 and 0 and 2 pointing to 1. And we have 4 with 5 pointing to it. 4 is the root. Now if I wanted to merge 4 with 1, it'll look like that. And so 4 now points to 1, and 1 is now -5 because there are 5 elements in there. And now, say I wanted to find 5. Remember that we have path compression, which is one of the optimizations here. So we find 5. 5 points to 4, and 4 points to 1. So what we do is we recursively call find on 5's parent 4, and 4's parent gives us 1, and so we know that 5 is now a part of 1. So all we have to do is reassign this pointer from the parent to the root, and so now 5 points to 1. And so when you find 5 next time, you don't have to go through the long path. You can just go directly from 5 to 1. And so that's how path compression and union by size help us make a tree that's shallow enough so that find works very fast. In fact, you can see, if you read Wikipedia or something, that find grows asymptotically like the inverse Ackermann function, which is very much just a constant. Yeah, it's the inverse Ackermann function is very slow. And so that's it for disjoint sets.